because it's enzyme nature, right? No enzymes, no ATP, you don't survive. What will happen if you continue at that high temperature or increase the temperature further is that in addition to proteins denaturing, the cell membrane will actually start to become unstable, right? Because the heat will actually start to cook and melt the membrane, the oil of the membrane, and the membrane will fall apart, and we call that thermal lysis, right? Lysis, splitting of the cell due to high temperature. Right, because the cell membrane is about the consistency of olive oil, right? You ever like get ready to fry something, you put some olive oil in a pan, and if you don't pay attention, the olive oil will disappear because you'll actually cook it and it will go away, right? And then you have a burning pan with nothing on it. That's what happens to the cell membrane, right? You get hot, the cell pops and the cell is dead. So at high temperature, proteins denature and the cell lyses. So what about cold temperatures? At lower temperatures, right, if we go backward, as the temperature lowers, enzymes are not working optimally, and that has mostly to do with the fact that thermal energy is not high enough for molecules to move. And so you have enzyme here, enzymes are not motile. Substrate here means enzyme is not going to encounter substrate. As you increase temperature, those things move around more and they tend to grab onto one another, right? So as we lower temperature, we slow molecular movement and the enzyme reactions happen slower and slower and slower. And you'll actually get to a point where that cell membrane will get so rigid that you can't get stuff into the cell anymore, right? Much like olive oil, if you take olive oil and put it in your refrigerator, it will solidify. That's actually how you can tell if you have really good olive oil. If it doesn't solidify in the fridge, it's garbage, right? Because olive oil will solidify. The membrane will solidify at lower temperatures. If it solidifies, good stuff can't get in, bad stuff can't get out, but the cell doesn't die. Notice, processes are so slow that growth cannot occur. Low temperatures do not kill microorganisms. High temperatures kill microorganisms. Low temperatures slow them down, right? Like all of the bacteria that we work with, guess what their optimal temperature is? 37 degrees Celsius, right? That's where we grow them. When we want to store them, when we know we're not going to be using them, guess what temperature we store them at? Negative 70 degrees Celsius. You store them at 4. We store them at negative 70. It doesn't kill them. When we're ready to use them again, we get them out of the negative 70 or negative 80, and we put them in broth, and we put them at 37 degrees, and they grow again. So low temperature doesn't kill them, right? So putting things in your freezer doesn't mean they're good forever, right? Even meat in the freezer has an amount of time that it can be there, right? It's a lot longer than the fridge, but it's not forever, because they will ever so slowly grow. So you can have food spoil in your freezer, and you can have food spoil in your refrigerator. It just takes a lot longer, right? What refrigeration and freezing did was bring the bacteria that would cause food spoilage down to here so that it would be safe for human consumption longer. So high temperature will kill cells, low temperature slows their growth. Notice there are no temperature degrees here, because not every organism on the planet likes it to be 37 degrees Celsius, right? That's kind of in the middle of all of the different optima, so we call him a mesophile, right? So this guy right here, who likes it right in the middle, 37 degrees Celsius, because that's where his enzymes are operating optimally, we call him a mesophile, because meso means middle. Like if you study Mesoamerica, right? That's the middle of the American continents. Meso means middle. So mesophile, phile likes it, right? Like Philadelphia, the city of brotherly love. Delphi means city. Philo means love. Philo means loves, right? So he loves it in the middle. So a mesophile is an organism who likes it at body temperature. Anybody who likes it above body temperature, we call a heat lover, a thermophile. And we have some that like it hot. That's about 60 degrees Celsius, right? Which you gotta keep in mind, these are degrees Celsius, right? Which those of us who have not grown up in Europe or elsewhere on the planet, because everybody basically, except for the United States, uses Celsius, times 2 plus 30. So 60 times 2 is 120 plus 3 is 150 degrees Fahrenheit is their optimum. We call them thermophiles. Some organisms really like it hot. Anybody who likes it over 65 degrees, we call a hyperthermophile. They like it really hot, right? Because hyper means up in degrees. Like a hyperactive person, right? Hyperactive. So we have mesophiles who like it in the middle, thermophiles who like it above the middle, and those who like it below the middle get this psychro attack. Notice it's not psycho, it's psychro, which means cold. They're cold lovers and cold growers. It's heterotroph, autotroph, psychrotroph. So you have this funny thing, right? Notice the psychrophile. And I would say, like your book, I kind of, take exception to things. What I would do, if this were me, I would draw the psychrotroph probably like this. Because a psychrotroph is an organism who is a mesophile, right? He likes it in the middle, but he can grow where it's cold. As opposed to a normal mesophile who can't really grow where it's cold. A psychrotroph is a mesophile who grows, we'll say, relatively well at 4 degrees Celsius. And guess which appliance in your house keeps things at 4 degrees Celsius? Your fridge. So a psychrotroph, like certain species of Pseudomonas, can survive and grow in your refrigerator, spoil your food, and then when you eat them, where do they grow best? In your belly, and they can make you sick. So psychrotrophs are a thing that we have to pay attention to, right, for food safety. Because if they can grow in the fridge, then it's hard for us to control their growth, and if they grow best in the body, then they can cause food poisoning. Psychrophiles, right, I would say are here. Those are organisms whose optimum is about refrigerator temperature. You don't have to worry about a psychrophile. Why do you think you don't have to worry about a psychrophile? Here's his maximum, and there's your body temperature. He can't grow inside your body. A psychrophile has to have it cold. A mesophile has to have it in the middle. A thermophile has to have it hot. And the crazy thing to think about is, right, so let's take our psychrophile, right, and we can go back, right? Let's go back here, now that we've nitpicked your book. At this temperature right here, what that's saying is it is so hot that his cell membrane falls apart. He thermally lyses his enzyme denature at 20 degrees. Cold room temperature, right? 20 times 2 is 4, right? That's cold. Not cold, but I mean, it's on the cold end, right? Room temperature is 25. But he doesn't get so cold that things stop until negative 10 degrees, because it's all relative. If he's built for 4 degrees, he has a really fluid plasma membrane, so that it will stay fluid even at really cold temperatures. He has enzymes that are really good at finding substrates, but those things mean that his loosey-goosey enzymes and his loosey-goosey cell membrane will lyse at very low temperatures. Alternately, the thermophiles have a really rigid cell membrane. They have lots of things in their cell membrane that help it to hold its shape even though it's hot. And they have really thermally stable enzymes. But what those two things mean is, at 40 degrees, his membrane is so solid he can't get rid of his waste and he can't take in food. Right? So it's all real, it's what you're made for, right? You're made for this, then your optimum is there. Anything below that, membrane gels, transport doesn't occur. Anything above that, and you might lyse. So it's all relative, and that's why the slide I showed you previously didn't have temperature on it. So you could superimpose these descriptions on every single one of those curves. Every one of them on the low end, no transport. Across the membrane, membrane is too solid. Every one of them on the high end, membrane lyses, proteins denature. So temperature, like I said, is the one that we think most about, right? Especially because we think about that in terms of food safety, right? Because organisms that can grow in our bodies can make us sick. And one of the very best ways that microorganisms know how to get into your body is to hitch a ride in your food, right? Clean water, clean food are two of the most important things for human flourishing. When you don't have access to clean water, people are today dying of diseases that aren't even seen in the developed world because we have clean food and we have clean water. So food is a great, we call it a vehicle for microorganisms. So we're gonna look for a minute at food spoilage, right? So here, we're gonna have a little home ec lecture. This is 2 containers of rice, right? One container of rice is about 6 inches tall. The other container of rice is about 2 inches tall. So preceding this, you made rice, right? You don't make rice, you boil rice, right? If you don't have a fancy rice cooker or an Instant Pot, you boil it on the stove. And then as you boil it, right, the rice gets cool, or the rice gets soft and it takes in the water and then it becomes like rice that we can eat instead of hard kernels of rice, right? And then you cool the rice, and then you eat it, and then you take the leftovers and you put them in your fridge, right? So I used to teach for years, I taught this class at night, because when my kids were little, it was much better for us, like my husband would work during the day and I was at home with the kids, and then he would come home and he would like pull his car up and I would jump in his car and leave, and then he would keep my car and sit up in car seats. I'm sure some of you felt this, right? So because I'm a good mommy, I would make dinner before I left for work, right? And I would come home, and class ended at 10, and usually I'd get home a little later because I gotta, get everybody cleaned up, and then I gotta do a couple things at work, and then I get home and it's like 11 o'clock. And I come in and this, whatever it is that I made is sitting in a big pot on the stove. And I'm like, I'm so tired. And these friggin' kids are gonna be up at 6 o'clock in the morning tomorrow. So I'm just gonna take the huge pot right off the stove. Because my husband's like, well, she probably didn't eat, so I'm gonna leave it on the stove so it's nice and hot so she can have dinner when she gets home. And I'm just too tired, so I put the lid on it and I stick that whole pot in the fridge. Maybe I'm the only one that does things like that, right? A diligent mother who maybe doesn't care about her microbial health, but is like, well, I don't want to tax my fridge, so I'm going to take it and I'm going to pour it into those nice shallow containers that you can buy, right? Your little Tupperware containers that you can get at the store. And I pour it out into those, and then I put those in the refrigerator, and they're only about this tall as opposed to my big stock pot, right? So here's what happens when I put those 2 things in the refrigerator. If I take my pot of soup or my pot of rice, why are we talking about rice? Because rice is grown in the ground, right? Have you ever seen a rice paddy? You actually pull it out, right? The rice is the kernels, right? It's in the ground. Well, there are organisms called Bacillus cereus that are also in the ground. They're my favorite microorganisms because their name is B. cereus. And B. cereus, right? Like, that's cool. In the ground, these B. cereus grow. They're spore formers, so they can survive cooking, and then they germinate, and they can cause B. cereus food poisoning, which is pretty serious food poisoning. It can make you very, very sick, right? So that's why we're talking about rice particularly, but we could also be talking about any kind of food. So I take the big giant pot, I put it in my fridge, right? It's still hot because it's been on the stove, and when I put it in the refrigerator, it starts to cool. And it cools systematically, and then in the fridge it gets to this, which anyone who's ever worked in the food service industry will know is called the danger zone. And the danger zone is the temperature range at which food spoilage organisms will grow. Because if we take this 15 to 45 and put it here, 15 to 45, there's our mesophile. So when you put it in the refrigerator, it hits this zone, and it cruises for a while, and it's danger, 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 not in danger anymore because now it's too cold for them to grow. If we do that with this container, right, the good mom puts her food into the shallow containers, puts them into the fridge, and it goes into the fridge and it cools and it goes danger, 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 not in danger anymore. So why am I the bad mom? Because my kids are going to be eating leftovers that were in the danger zone from here to here. Hour 3 to hour 8, that's 5 hours. Biotic potential, which is dependent on generation time. E. coli go through 3 generations an hour. In 7 hours, 1 cell equals 1 million cells. So what have I done to my food? I've allowed it to stay in the danger zone for long enough that there are going to be a heck of a lot of microorganisms inside that food. Now, if I cook it really hot, sure, I could kill them. I'm not telling you to do that with rotten food, right? Don't boil rotten food and eat it. Not a good idea. But look at that, right? So 5 hours in the danger zone. Over here, from here to here. Less than an hour in the danger zone. Not even 3 generation times. So 1 became 2, and 2 became 4, and 4 became 8. So we have a much lower microbial load, perhaps low enough that it does not meet the threshold for food poisoning. And that's why you put your things in shallow containers and you put them in the fridge. Yes?
So I also, like, when they say when food's like hot, still don't cover it. Or like seal, like put Tupperware lid on it, let it cool first, and then stick it in the fridge. Is that true?
I would say from a microbial standpoint, it should go into the fridge as soon as possible.
Oh, even if it's hot, okay.
Yeah, because you're getting it into the cold area. Now what you could think is, well, if I seal a plastic container, it's harder for the hot air to get out of there, so you could like put loosely or something. A lot of what people think about like when to put things in the fridge is not based on microbial stuff, it's based on like how difficult it is for the fridge to work. Because you're putting hot things in there and the fridge is, right, you'll hear that it's overworking your appliances. So a lot of it is like different wives' tales about things like that, like let it cool to room temperature and then put it in the fridge because it'll cool faster. But well, yes, but you also left it for 12 hours on the countertop, at which point you're really in the danger, right?
Yeah.
So from a strictly microbial perspective, food should go from the stove into the fridge. It shouldn't cool. Right? I mean, but there is time. It doesn't mean that, you're going to die, right? You're all alive. And I'm sure that there's a lot of things that you've eaten, right? You've been to a picnic. Like, I have a half a sandwich sitting on the table waiting for me because I don't like it when my half a sandwich that was warm gets cold before I eat it. So I was like, don't put it in the fridge. And my husband's like, you're disgusting. I'm like, oh, there's no mayonnaise on it. I'll eat it. Right? I had it for lunch, I'm going to have it for dinner. Don't, it's like most mom things. Do what I say, not what I do, right? So that's why we care about food spoilage, right? Because this area here is the growth of mesophiles, and guess what else is that temperature? You are. So if they grow, we're going to learn about something called an infectious dose, and that's the minimum amount of microorganisms it's going to take to make you sick. And this allows them to reach that threshold so that they can make you sick, right? All right, so temperature, that's the big one. We're actually going to look at 4 physical growth requirements for microorganisms. Temperature is the big one we think about first. The second is kind of a weird one, and it's really salt. Salt, because salt causes osmotic stress on cells, right? Like, do you ever eat a bunch of sunflower seeds? My son plays Little League. They love to like sunflower, massive amounts of sunflower seeds. And I'm always like, no thanks, I don't want any sunflower seeds because they chap, my lips get chapped, right? Because the salt sucks the moisture out of your lips and makes them chapped, right? Because salt dehydrates things. Salt will cause water to leave, right? Because water wants to dilute salt. So here's your problem. Every cell in a natural environment, not your cells because you're a giant baby and your cells get protected, but every other cell is constantly experiencing osmotic and turgor pressure. High salt that makes their water want to leave, and then that salt getting washed away and diluted, which makes water want to rush into your cell. So we say osmotic stress, that's salty stress, that makes you shrivel up. So I made the word osmotic a little. So you think a cell under osmotic stress shrivels up. A cell under turgor stress will pop. And if you are not part of a multicellular organism who perfectly bathes its cells in isotonic solution, you are going to be a cell that is constantly trying to fight this salt wanting to go in, water wanting to go out, salt going away, water wanting to rush in, and you're constantly being shrunken and blown up and shrunken and blown up and shrunken. So you have to come up with a way of withstanding this constant change in the saltiness of your environment, right? Because in a perfect world, it would be isotonic, and that's what we try to do for bacteria when we grow them in the lab. Right? If you were to drink that media, it would taste a little salty to you. Because we're trying to balance the amount of salt in the media to the amount of salt that's inside the cells. And for most cells, it's just like you. It's about 0.85%. Which is why if you ever get an IV, your saline is 0.85%. You know what I learned today? The pH of that saline is 5.5. Isn't that crazy? I learned that because I was listening to my husband listen to lectures on like traumatic field, like injuries in the field where you give somebody like a bunch of saline and you actually jack them up because you change the pH of their blood and their blood can't clot anymore. And I was like, what? That saline? I mean, you'd think it'd be neutral. That's what I would have thought, right? It's not. So, in a perfect world, right? Water comes in, but water is also leaving because the water that wants to come in is offset by the water that wants to leave. In a hypotonic environment, right, there's lots of solute inside the cell because it's basically water outside. What does water want to do? It wants to dilute what's inside and you will pop. You will go kablammy and you will die. If you are in an environment where there is tons of salt, all of your water will leave, and when your water leaves, the cell shrivels up. They can't do anything because most everything that happens in your cell has to happen in water, right? They've been exploiting this for thousands, probably years in food preservation, right? Before there were refrigerators, people ate salted meat and smoked meat. Why? To dehydrate it so that stuff couldn't land on it and grow, because any microorganism that lands on beef jerky gets all the water sucked out of it. Even sugared things will last longer, right? So this is the issue, and what you want to do when you're constantly in one of these two is maintain your shape and your size and the amount of water inside you. So what you have to do basically is constantly be able to change your internal concentration. But you don't want to add salt inside, because salt is bad for you. Salt ionizes and gets crazy, right? So what they do, right, they have a cell wall, which keeps them from popping, and then they make these things called compatible solutes. Right, because a solute is something that's dissolved in water or solution. And so for every solute outside, they have one inside, and that balances and allows them to hold on to their water so they don't shrivel up. We call them compatible solutes. Solute meaning that it can dissolve in solution. Compatible meaning it's not going to jack you up. It's compatible with your cell. And compatible solutes are super cool because they balance the salt that's outside, so you stay the right shape and the right size, right? It makes it seem like it's isotonic because you've got all these compatible solutes in there. Let's say for every like little black sodium chloride, you've got a little red compatible solute. And so everything is balanced. And when the outside changes, these compatible solutes are really good at just going outside of the cell. So they'll come in and they'll go out. It's really easy to change them, right? So they increase the halotolerance of the cell, halo meaning salt tolerance of the cell. They have a very high solubility in the cell, so they won't come out of solution and get in the way. They have a high permeability, so they'll leave the cell when they're no longer necessary, and they're metabolically inert. They don't do anything, they just sit there. So they're just like these little bobs, they're bobbing around in the cell, right? When they're no longer needed, they go outside. When they are needed, they come back inside, right? And they don't do anything. All they do is keep water where it's supposed to be, and they allow cells to stay normal in environments that are either hypotonic, where they would pop, or hypertonic where they would shrivel up. Now, not all cells have a lot of compatible solutes. Those cells that have a lot of compatible solutes are halophiles. They like salt because they have all of these compatible solutes that allow them to not only withstand, but thrive in high salt environments. Now, you may think 3% salt, you're like, well, that's nothing. I mean, that's the ocean. It's pretty salty, right? I mean, if you swallow ocean, you'll vomit because that's so much salt that your body's like, can't let that in, right? And you get sick. They love it, right? They live in 3%. Lower than that is not optimal. Higher than that is not optimal. But notice they have a much smoother curve here. No like steep drop off. Because the amount of denaturing and stuff like that is not affected by low or high end, right? So we have halophiles, which are like ocean dwellers. They're marine organisms. And we have extreme halophiles. These dudes are nuts. You know, so the saturation point of salt in water is 30%. Anything higher than that and salt will just crystallize. They love it. They'll like grow on the salt crystals in the Dead Sea. It can't possibly get any saltier than that because the salt just comes out of solution. And they require at least 5 times as much salt as the ocean. So it's crazy, right? Super salty, super salty. So we have extreme halophiles, right, that like it above the ocean. Halophiles like it where the ocean is. We have non-halophiles, that would be you, me, E. coli, most everybody that we work with here. And then we have halotolerant cells, who are kind of like these guys, right? Unfortunately, different people name different things. We could call a cyprotroph a cyprotolerant organism. And we can call a halotolerant organism a halotroph. Both of those terms mean I can do it, but I don't prefer it. So halotolerant, they tolerate salt, but they don't prefer salt. Notice they grow best at 0.9% and they go down. These actually do include some of your normal flora. Staphylococcus is a genus of bacteria who are halotolerant. They will grow, right? We routinely culture Staphylococcus in 10% salt broth. So about 3 times as salty as the ocean, right? Because if you ever lick your arm, don't do it now because you're in a lab, plus who wants to watch you lick yourself, right? But it's salty because you have salt on your skin. So it makes sense that organisms that live on your skin can withstand salt. They don't love it. They're not halophiles, they're halotolerant. They would rather not have salt, but they grow just fine in the presence of salt. So temperature is an environmental concern. Salt is an environmental concern. Incidentally, we will be looking in lab 11 at temperature requirements of organisms. We will not be looking at salt because of the difficulties that go along with making media that's got a high salt concentration. It tends to ionize and cause all the good stuff that they like to eat to come out of solution, so it's a little bit difficult to work with, so we don't have a lot of high salt stuff. So we're not going to be looking at salt optima, but we will look at temperature optima, and we will look at 2 other physical characteristics of the environment, including, pH. So neutrophiles, as their name suggests, are organisms who love it neutral. That would include you and me and lots of microorganisms. Organisms who like their pH to be low are called acidophiles. And organisms who like their pH to be high are called alkalinophiles, right? So anything above 7 is alkaline or basic. We call them alkalinophiles. Anything below 7, acidophiles, right? They like that. Now, one thing we need to remember, I know we said we're not, looking at chapter 2, which was our chemistry chapter. When you look at a pH scale, you want to keep in mind that every number change is a 10-fold change. So pH 7 to pH 6, pH 6 is 10 times as acidic as pH 7. And pH 5 is 100 times as acidic as pH 7. And pH 4 is 1,000 times as acidic as pH 7. Just to give you an idea of the wide range, even though it doesn't seem wide, because you're saying, well, that's just 1 to 5, who cares? Do you know what your pH range is? You know what your blood pH is? 7.35 to 7.45. If you change the pH of your blood outside of that very narrow range, you will hyperventilate and go into respiratory and cardiac failure, and you will die, right? Because of all sorts of fun physiological things that we're not going to talk about. These guys, right, so let's take, for instance, the neutrophil. E. coli is a great example of a neutrophil. You can take E. coli and plop him anywhere from 4.5 to 7.9. So 1,000-fold change in acidity. His internal pH will change by 0.1. So they're very able to moderate their internal environment, right? Do you see this is a constant theme? They can moderate their internal environment even when the outside environment is changing drastically, because they have to. They're not a multicellular organism who can baby its cells like we can. We can baby our cells. They can't baby their cells, right? They can't be babied. So how do they handle wild changes in pH?